Welcome back to The Explainer. Today, we're not looking at the Earth's surface as some static, boring painting. No, it's a highly dynamic, ever-changing system. We're diving into something geologists call mass wasting. Now, you might just call it a landslide, but mass wasting is actually the broader, way more precise term for any downhill movement of rock and soil driven by the relentless pull of gravity. It's literally happening constantly all around us. And honestly, understanding the science behind it is absolutely vital for anyone living near a hill, a mountain, or a coastline.
So, here's our agenda for today. First, we'll break down the physics of slope failure. Second, how water triggers instability. Third, classifying mass wasting events. Fourth, identifying landslide anatomy. And finally, mitigation, or defending the slopes.
All right, Section 1, the physics of slope failure. To truly grasp mass wasting, we kind of have to start treating the Earth's hills and mountains as literal battlegrounds. So I want to pose this fundamental question to you. What keeps a mountain from falling down? I know, it sounds like a child's question, right? But the answer is the absolute foundation of slope stability. Gravity is this constant force pulling everything toward the center of the Earth. So why isn't every mountain just a flat pile of rubble? Well, the answer lies in a central physics conflict that is happening every single second on every single slope. Imagine a massive block of rock sitting on an incline. The force of gravity acting on that rock actually splits into two distinct components. First up, we have the shear force. This is the driving force, the bad guy, if you will, actively trying to push and pull that material downslope. Opposing it, fighting back, is the normal force. This is the resisting force, pushing the rock directly into the slope, and that produces friction. The relationship between these two, that's called shear strength. As long as the normal force, the friction, is greater than the shear force, the mountain stays put. But if the slope gets steeper, the shear force proportionately increases while the normal force decreases.
And that brings us to a really critical threshold, the angle of repose. By definition, this is the steepest angle at which rock and soil material is stable and won't move downslope. Think of it as perfect equilibrium. When a slope sits exactly at its angle of repose, the shear force is perfectly balanced with the normal force. If you tip that angle just slightly steeper, the shear force wins and the material starts moving downhill. Now, this angle varies wildly depending on grain size and composition. Dry sand, for instance, might max out around 30 degrees, cascading down until it naturally settles right back at that perfect angle of repose.
Moving on to Section 2, triggers, water and instability. Now, the angle of repose isn't some permanent guarantee. Let's introduce the variables that disrupt this delicate balance, our primary antagonists that compromise slope stability and tip the mathematical scales in favor of gravity. When we look for the ultimate saboteur of slope stability, we really have to talk about pore pressure. See, when water infiltrates a slope, it fills the empty air spaces or pores between the grains of soil and rock. This exerts an outward pressure. By actually pushing the grains apart, pore pressure actively decreases the friction, that vital normal force we just talked about. When friction drops, shear strength just plummets and the slope is completely compromised. The crucial point here is how water acts on a microscopic level. Honestly, there's no better way to understand this than the classic sandcastle analogy. If you try to build a sandcastle with completely dry sand, it just crumbles, right? But if you use damp sand, the water adds surface tension and cohesion, allowing you to build vertical walls. You're effectively increasing the angle of repose. But, and here's the kicker, if you add too much water, the sand becomes saturated. The pore pressure totally overwhelms the friction, completely destroying the shear strength, and your sandcastle instantly collapses into a puddle. This exact same principle applies to massive mountainsides. Let's review the primary triggers that inject this instability. Increased water content from rapid snowmelt or intense rainfall is definitely the most common trigger. But we also have seismic events. For example, the massive 1959 Hebgen-Rake rock slide in Montana was triggered by earthquake shaking that violently weakened the slope's shear strength. And then we have oversteepened slopes. This can happen naturally, like a stream undercutting a bank, or artificially when we humans cut into the bottom of a hill to build a road or parking lot. If you remove the support at the bottom, you instantly destabilize the entire system above it.
Okay, Section 3, classifying mass wasting events. Once the system is destabilized, gravity completely takes over. But mass wasting isn't just one type of event. It's a whole spectrum of geological movement. We classify these events based on two main criteria: how it moves and what is moving. Think of it like a grid. On one axis, we have the material. Is it solid bedrock, loose coarse-grained soil, or fine-grained earth? On the other axis, we have the movement type.
Falls are abrupt, free falls of rock. Slides move as a cohesive mass along a surface. Flows move rapidly like a fluid, usually mixed with abundant water, like a devastating debris flow. And creep is this imperceptibly slow, gradual downhill shuffle of soil, usually caused by freeze-thaw cycles. Let's zoom in a bit and compare two very specific, very important types of slides. Rotational slides, often called slumps, move relatively slowly along a curved, spoon-shaped rupture surface. But translational slides? Oh, these are incredibly dangerous. They move rapidly along a flat, distinct plane of weakness, like a sedimentary bedding plane that runs parallel to the slope. A terrifying example of this was the 1925 Gros Ventre event in Wyoming. A river undercut a layer of sandstone, heavy rain saturated a layer of shale underneath it, turning it into a slick slide board. And boom, 38 million cubic meters of rock translated rapidly down the slope, damming a river and creating a deadly flood. Section 4, Identifying Landslide Anatomy. So, when an event like Gros Ventre happens, how do we study it afterward? Well, landslides leave behind very distinct geological signatures. It's almost like a crime scene. When you look at a hillside that has failed, look first for the main scarp. This is the steep, crescent-shaped cliff at the very top, marking the uphill tear where the material actually broke away. The surface it slid on is the slide rupture surface. Down at the very bottom, marking the maximum runout distance of the debris, is the toe. And all the material sitting in the middle? It usually forms hummocky terrain. It's this undulating, lumpy, uneven topography that is an absolute dead giveaway that the ground has been severely disturbed. You might even see sag ponds where water collects in the depressions, or tilted trees, marking the chaos. Finally, Section 5, Mitigation, Defending the Slopes. We know the physics, we know the triggers, and we can identify the aftermath. So how do we actually protect human populations from these gravitational inevitabilities? Well, engineering offers a sequential protocol for slope defense. Step 1 is always about the water. Because pore pressure is the main trigger, diverting and draining water away from slide areas is the most common and effective defense. We use tarps, plastic sheeting, and deep drain wells. Step 2 is physical reinforcement. If a rock face is fractured, we'll drill long steel rock bolts directly into it to pin it back, or spray reinforced concrete, called shotcrete, to hold the whole thing together. Finally, Step 3, if we can't stop the mountain from falling, we build structures to catch and divert the runout, things like stretchable catch fencing, diversion channels, and check dams to slow down debris flows before they hit a town. To really understand why these defenses matter, I want you to just think about this massive number: 65 million. In 2013, at the Bingham Canyon copper mine in Utah, 65 million cubic meters of steep, terraced rock collapsed in a massive landslide. It was one of the largest non-volcanic landslides in recorded history. This number grounds our data in terrifying real-world stakes. The sheer force simply overwhelmed the normal force on a truly catastrophic scale. But here is the incredible part, captured perfectly in this quote from our source data. Radar systems maintained by the mine operator warned of the wall's movement, preventing the loss of life and limiting the loss of property. Because they had advanced monitoring protocols continuously scanning for microscopic creep and instability, they evacuated the area. 65 million cubic meters of rock fell, and not a single life was lost. It's amazing, right? This brilliantly illustrates that while we absolutely cannot turn off gravity, human ingenuity, monitoring, and geological threat assessments can literally save lives. And that leaves us with a final, provocative thought. We live on a dynamic, highly active planet where sheer force and gravity are working 24 hours a day, 7 days a week to pull the high ground down to sea level. As our populations expand, we build infrastructure in increasingly steep, rugged terrain. Can our engineering and mitigation protocols forever outmaneuver the Earth's relentless gravitational pull? Or is it really only a matter of time before the angle of repose catches up with us? It's a fascinating battle between human engineering and nature's math. Thank you so much for exploring this with me today. I'll see you in the next explainer.